Hello, this is Math 2231 coming to you from the College of DuPage for summer of 2020. The topic of this lecture is review, third lecture of 4, doing a review and more. Calculus is the study of limits, and so it is important that you recall not only that, but the definition of a limit. This is what we showed last time. And so we say the limit as x tends to a of f of x equal L, provided we can make f of x as close to L as we want for all x sufficiently close to a from both sides without actually letting x be a. Now this is not the formal epsilon and delta definitions, but we will get to that soon enough. You really want to probably pause and read this carefully, but the definition tells you as x gets close to the limit point, from either side, the value of y equals f of x remains arbitrarily close to L. Kind of a subtle concept. So here's an example. We are to use numerical estimates to estimate the value of this expression. So it's the limit as x tends to 2 of this quotient. Now note that if you put 2 into the top and 2 into the bottom, you get 0 over 0. 0 over 0 is an undefined term. It is not 1. And the fancy math word for this is an indeterminate form. You know what to do. Let's see how you did. Well, you plug in a bunch of numbers, approaching 2 from the right and approaching 2 from the left, and you look at these and you say, oh, it seems to be getting close to 4. Now, if you look at the graph of this, we realize that 2 is not in the domain because you get the 0 over 0, and so you actually have a hole in the function. But as we approach 2 from the left, the y value gets closer and closer to 4, and as we approach 2 from the right, it gets closer and closer. It does not matter that it is not defined there. Next example, you want to estimate the value of the limit as x tends to 2 of g of x, where g of x is this piecewise defined function. You know what to do. Let's see how you did. Well, you realize quickly that this is essentially the same function, except for x equal 2, and when x is equal to 6. There should have been a dot here. Let's just pretend, in fact, my little pointer is the dot. And so that's what happens. It's essentially the same function, but the same thing happens as you approach from the left and from the right. So it is still 4. It didn't matter that the function was now defined and defined to be something else. Next problem. We want to estimate the value of this. This is the limit as theta goes to 0 of 1 minus cosine theta all over theta. Now in calculus, class angles are almost always, except for the occasional word problem, expressed in radians. There is much trigonometry in this calculus course, another authentic prerequisite. My point is these are real numbers that you're approaching here, and the theta is radians. Let's see how you did. If we plug in a bunch of values, here we're approaching 0 from the right, here we're approaching 0 from the left. These numbers are getting closer and closer to 0, so this would allow us to guess that the limit has the value of 0. We want to estimate the limit as t tends to 0 of cosine pi over t. You know what to do. Let's see how you did. Well, you could have picked some values, but depending on what you found with the values, you could have a mistake like this one. If I happen to pick these values, I would mistakenly conclude that the limit is 1. It is not 1. And here I show that I can pick numbers that are all less than the size of these numbers, but get totally different answers. So what that means is the function is oscillating. So it's going like this, but it's going up and down wild and crazy like this as you get close to 0 from both sides. So you see, we do not get close and stay close to a fixed number. This limit does not exist. This behavior is called oscillation, and this would be called an oscillatory function. Here we're to estimate the value of the limit as t tends to 0 of capital H of t, where capital H of t is defined in this piecewise manner. You know what to do. Let's see how you did. This function is either called a step function or the Heaviside function. That's why we call it H, honoring our Oliver Heaviside. It's used in applied mathematics to model discontinuity such as an air conditioning system kicking in. But you see here, if we think about the graph from the right would tell you that we expect this to be 1. From the left it is 0. This limit does not exist because the limits from each side have to be the same. Okay, so we've seen that there's limitations to both graphing and numerical calculations. So we will be focusing, not exclusively, but certainly focusing on analytical calculations of limits, and soon. And we will use new vocabulary and notation to do this. We'll talk about a limit. That is the right-handed limit. This is limit as x tends to a from the right. That's denoted with, looks like a little exponent and a plus sign. F of x is equal to L. If we can make f of x as close to L as we want for all x sufficiently close to a with x greater than a. And we have a left-handed limit. Similarly, we say the limit as x tends to a from the left. The exponent here is minus, so we're coming from the left, of f of x equal L if, and it's the same kind of words, but for x less than a. And so here is an example where we get to practice this new vocabulary, and this is Embedded Quiz 1. That means this will be due on Blackboard 24 hours after the post. This is 10 points to be found or lost. See you in